Hey, there we go. Oh, sad. You only get half the learning, I'm afraid. So this is a bit of work called Inroads in Autonomous Network Defense using explained reinforcement learning. It's a collaboration between Imperial College London and the Alan Turing Institute. So a bit of, hopefully, on the next slide. There, oh, no, that's too many. Spoilers, there's going to be reinforcement learning. So for those of you who get bored halfway through my presentation, these are the main things I'm going to cover. So we're going to do a bit of background on reinforcement learning. We're going to talk a little bit about the setup, so network defense as a game, how we model it, the things that we assume. Then we're going to talk about the solution that we come up with for dealing with multiple adversaries in the network. And then we're going to see how well the solution does and see if we can do a little bit of explainability around it as well to see what kind of features are important in learning. So yeah, reinforcement learning. Who here knows about reinforcement learning? Hands up. Oh, this is unfortunate. You're all going to get my explanation of reinforcement learning. I'm sorry. This is my favorite explanation to give. It's a mouse in a maze. So why is reinforcement learning a lot like a mouse in a maze? Well, you have an agent. That's our mouse, and mice, as everyone knows, famously they exist in mazes, which are environments, but mainly they like cheese. Although for anyone who's ever had a mouse problem, they don't like that. They like peanut butter. Top tip. So the mouse is going to learn a policy by interacting with the environment, by taking a series of actions. So in this instance, it's going to be north, east, south, or west steps. And it's going to update its state, which is the XY coordinates within the maze. So this was actually done, this example was given in the keynote this morning by Claude Shannon in 1952. He was able to get a little mouse to move around and find its way out of a maze by reinforcement learning, which is pretty cool. So you may be more familiar with the reinforcement learning loop, which is something like this. So it's a kind of a mapping between states and actions. Is a nice way to think about an agent. Now this, I'm hoping might work. Yeah, there we go. So this is a kind of a cool example where we have a humanoid kind of object that's able to do muscle contraction like things and learn to walk. If it goes to the end, it will run. No, okay, we're going to do the cool little history of reinforcement learning instead. So yeah, 1992. When things start to get good, and then deep learning explodes with AlphaGo 2015. If you've not seen the AlphaGo documentary, it's on YouTube. It's really good. I won't spoil anything, but the results are really cool. And then more recently, we were able to, or I say we, the reinforcement learning guys, were able to surpass human level performance on Gran Turismo. And as you probably come across Alpha Tensor in the last month or two, it's really good at doing games. So why do we want to do reinforcement learning in security? Security is hard. I'm sure everyone in this room probably is going to acknowledge that. And it's often about playing games or things which are like games. There's been a lot of talk of cat and mouse and kind of one-upmanship of attackers and defenders. Reinforcement learning, a lot of talk about labeled data. We don't need labeled data in reinforcement learning. We just need something to play with. And as well, that thing is an environment, so we interact with that. And yeah, reinforcement learning is able to go past human level abilities in games. Why can't we do that in security? So a little bit of background on some stuff that we use. This is PPO and Curiosity. Obviously, I don't need to explain this, and you'll understand exactly what's going on from this one slide. No? Okay, fair enough. So PPO, or proximal policy optimization, is a deep learning method to solve the reinforcement learning problems. It's a policy gradient method, so traditional kind of stuff there. But what's nice about it is that it scales a lot better with big environments, real world problems. And it's able to do this by taking in lots of data in batches, learning on it, and then discarding it. And one of the impressive things about it is it's able to clip the gradient updates so that it doesn't kind of do something completely absurd and training's a lot faster. So curiosity as well is a really fascinating idea which tries to motivate how agents explore their environments. So this is able to kind of incentivize them to do that via a intrinsic reward based on how often agents visit states. And we use the intrinsic curiosity module, or ICM, which is particularly cool because it's able to kind of get rid of the noise from within observations in states. So you can kind of think about it as like, if you were to do a computer vision problem, but you've got leaves kind of like blowing through that, we're able to ignore the leaves and look at kind of what's beyond what we're actually dealing with. So yeah, network defense as a game. So we use an environment called Cyborg. It's developed by a group of cool researchers down in Australia, and they use it in a couple of different challenges called CAGE, which stands for the Cyber Autonomous Gym Experimentation. And within it, you have a couple of different red agents adversaries. So you've got your beeline attacker who beelines straight for some kind of objective. They have prior network knowledge, and they're able to move through it very quickly. And you've got the meander. It's a bit slower. It's more of a traditional attacker who's just got into the network and is making its way through. Yeah, sometimes things don't work quite as we intend them to, both on the blue and red side of things. So sometimes things are going to go a bit wrong. So this is the network that we're going to use. And so within it, we've got 9 different kind of hosts, and we've got 4 different servers. So we are going to sit in the middle. We're able to kind of do some interesting stuff, and we'll get into that in a moment. But we've got our red agent, our adversary, which we kind of allow it to have an initial foothold in the network, because otherwise we're able to do very trivial solutions where we just completely cut it out and nothing interesting is going to happen. And we've got an operational server, which our kind of adversary is then trying to get to. And they make it way all the way through and onto the server. So what can the red agents do in order to make it the way through? So this is all stuff which is based on the attack framework. So we've got discovering remote services, network services. So this is Nmap kind of style of things, discovering or exploiting stuff. So manual, metasploit, that kind of side of things. And then escalating privileges, kernel exploits, and impacting the operational server, which is trying to reach to stop us from keeping things safe. So just general DDoS or DOS. So this is pretty bad. What can we do? We can do a bunch of different stuff. So we're able to monitor the network level, packets, connections. We can look at a specific host, see what processes are running, what files are open. Set up a honeypot on the network of a decoy of one of the hosts running whatever service it is, remove users because some users might be malicious, or just reboot a box back to its safe kind of checkpoint. So we need kind of a reward signal to train our agent. Now, there are no winners in security, right? As you can see, you can only lose. Rewards are negative, they're penalties. So we kind of trying to disincentivize the defensive agent from the attacker getting it onto like the operational servers and servers in general, and user level and admin privileges on hosts. You also see there's a bit of a penalty as well for if a red agent is able to make it onto an operational server and then just impact our ability and our performance. So that's pretty bad. And we also have a penalty for restoring, so rolling back a box, because people who are like normal and not security get a bit annoyed at us when we do stuff like that. So what are we able to see as a defensive agent? So we're able to represent the entire network, and you're going to have to bear with me on this, in 52 bits. Yeah. But what does this mean? So each different host and server is 4 bits. So that is 2 bits to indicate if an adversary has tried to scan a box, if that's known, unknown, or has failed. And then the other 2 bits are for privileges. So if we've got an attacker who's able to get user level or administrative privileges, we kind of want to know about that. So that's how we're going to represent it. So RL to the rescue. Let's solve this. So we come up with a specialized tailored defense to deal with each of the adversaries that we're going to see. So we tried a whole bunch of stuff, and empirically, this is what works. So for the meander, we're able to have a slightly larger network, but we don't deal with any kind of like incentivized exploration because there are less edge cases in the behavior of the agent, because it's going to try and explore more and do different things, as opposed to the beeline, where we do see kind of this very like concise behavior, and occasionally it deviates. So we want to make sure that our agents are able to deal with that. So we use curiosity. We also are going to implement kind of two variants on this. So we're going to include additional information. So this is going to be the prior action knowledge. So if we took an action, if we took a restore action to try and reboot a device, did that actually work? That seems like it's pretty important to know. Although interestingly, it's not for the meander agent. And then we also do a little bit of stuff with the state representation. So instead of representing it as 52 bits, we take them as float values. So taking them as 12 float values. So we kind of need to know a little bit more about our agents, our adversaries, sorry, in order to really tailor our defense. So as we can see here, this is the first 4 steps of the game that the red agent will take when it's allowed to do whatever it wants. So this kind of like Death Star looking thing on the left is kind of a depth first approach. So it's trying to penetrate as quickly as possible by going through any of the users and then trying to get administrative privileges. On the kind of right-hand side, on the meander, it's trying to go breadth first. So it'll go, okay, well, let me scan all these things. Let me get user access. Let me get administrative access. So how can we use this? Well, we can have one agent to rule them all. So we need to be able to select which of the tailored defenses that we've got to deal with the adversaries. So we come up with 2. So in prior work, using the same kind of environment and adversaries, there is a deep learning PPO model, which is able to do this, where you kind of look at it and go, well, you can kind of see what the adversaries are doing. Can we do it slightly more efficiently? So we define a bandit-based controller and a heuristic as well. So yeah, our multi-arm bandit, or a little friendly octopus. So who's familiar with bandits here, if you're familiar with reinforcement learning? Slightly less. Okay. So in the multi-arm bandit setting, it comes from the one-arm bandit of slot machines. So the game is, I have 10 slot machines in front of me, and I've got to pick the best one that's going to give me the most money out. Now, this assumes that there's like no notion of state, right? Which is fine in that setting, so that'll work. But for here, there is a notion of state, and if we ignore that, our adversaries are probably going to be able to get around our defenses. So what we do is take the example of the slot machines in the casino. It's kind of like walking into a casino, learning in one casino which machine to choose, and then in a second casino, learning which machine to choose. But now imagine you are in one of the casinos and you don't know which one it is. So the way in which we're able to get around this is observe the states that we're seeing and train bandits for each of those states that we see. Now, you could try and do this by a kind of regression or SVM, but it's a lot easier to do this because we're able to have less data and we're able to train stuff again afterwards. So then heuristic wise is actually fairly simple. We just check to see if there's multiple scans going on. And if there is, we know that that is a meander because it's trying to scan everything first. So that's great and all. How well does it do? Good question. I'm glad you asked. So in training, we're going to kind of see some kind of interesting things. So in the meander case, we train all of the variants that we have. And there's a very much a clear winner, like the base model of the PPO doesn't, or clearly outperforms everything else. If you look to the left-hand side against the beeline adversary, that's a bit harder to tell. you might be able to see there's a very, very slight uptick of red and green towards the end of training by the end of 10 million time steps. That's going to be good, right? It's going to work well. And then for our bandits, this is actually test results. We're able to do 100% accuracy with the heuristic and bandit methods versus the PPO with curiosity, which was used in prior work. So how well does it do against all the adversaries as an end-to-end model? So as we can kind of see here, the top two results are our implementations of bandits and heuristics and the sub-agents that are specially trained. They're able to outperform all of the other things. So that's our sub-agents with the baseline from prior work, and also a complete baseline from prior work. So interestingly as well, our solutions don't ever have the operational server compromised. The red agent never makes it on there, never does anything malicious to impact performance. So this is great. Let's have a look at what is important for agents to know. So we perform an ablation study. So we take the three main types of observation, the adversarial access, the scan that they have as well, and then the previous action. Note that for the meander agent, it doesn't actually use that in the observation space, but the graphs look pretty with three, and I like the symmetry. So yeah, the main thing here is that access and being able to see what the adversary has and what access it has, user, administrative, nothing, is unsurprisingly pretty important. But kind of surprisingly in the middle though, the scan kind of obliterates to some extent the defensive capabilities of our state representation. So this is taking it as floats instead of bits. We think that that's possibly to do with the way in which the neural network is trying to take it as input, and the magnitude of it, maybe. And then finally, we're going to have a quick look at SHAP values. So this is an explainable AI kind of technique called Shapley additive explanations. They really backonymed it, but it works. So what does this do? It tries to look at the important features within the local importance. So if I vary one feature, how much does that matter for that one feature? And how does it matter within the whole feature space as well? So what we've got going on here is it kind of confirms what we saw before. So the adversarial scan has a quite large distribution on the B-line defense with the state representation, and as well on the B-line with action knowledge representation as well. And yet the previous action doesn't really seem like it's making as much of a contribution. I'd argue that it does, because as we see from the prior table that you saw, it does seem to improve performance as well. So I forgot to put a slide in on future work and conclusions. So future work and conclusions is then that reinforcement learning is kind of a cool tool to use. Is it going to replace SOCs and sysadmins tomorrow? No. Will it ever? Probably not. Will it be useful for analysts and sysadmins and SOCs? Probably it will. Future work. So there's a couple of assumptions that we've made here on adversaries and network structure that would make interesting experiments for the future. So with that, thank you for listening. Any questions?